Hello, and welcome to the lecture for Chapter 13 from Conceptual Physical Science. This chapter really ties together well with Chapter 12, which I said in the previous lecture video when I had lectured on Chapter 12, because these two chapters represent a bridge from physics over to chemistry. Now, that said, this chapter in particular, talking about the atomic nucleus, is really a field that is mostly covered by people who say they study physics. So this is all about nuclear physics, as it's often called, studying the very inside of the atom. Now, of course, chemists care about atoms, but they don't so much care about the nucleus. But also, it's natural that we cover this chapter after chapter 12, the last one, where we introduce the atom as a whole, because essentially we're zooming in. We talked about the whole atom and the electrons around the atom and the periodic table, how we group together atoms in things called elements. But what happens in that very center, that tiny, dense center of the atom? Well, it turns out a lot of fascinating things happen there. That's how we can explain processes like nuclear fusion and fission, like in power plants or inside the sun. And we can even talk about radioactivity, like elements that produce radiation, and of course, which are harmful to our health. So lots of really applicable stuff you've probably heard about in the news. So let's get into our table of contents. So we're going to start off by actually introducing radioactivity. What is it? Okay, it comes from the nucleus, but what is it? How do we classify it? What are the types of radioactivity? Then we'll talk about the atomic nucleus itself and the strong nuclear force, which I've hinted at a couple times. Suffice to say, it's the force that holds the nucleus together. But we'll come back to that in just a moment. Then we'll talk about a little mathematical aside, which is the idea of, the idea of calculating half-lives. That's how you can talk about how much of a radioactive sample remains after a certain amount of time. And transmutation, which is just the idea of one element changing into another because of changes within the atomic nucleus. Okay? Then we'll talk about radiometric dating, because since a half-life is a period of time, how much of a sample that is radioactively decaying remains in a bone or a rock can tell us the age of that bone or rock. So that's called radiometric dating. Then we'll get into nuclear fission. That's what power plants do. That's what most nuclear bombs do, like the ones that were dropped on Hiroshima and Nagasaki, right? That's nuclear fission. That is breaking apart of the nuclear, the atom nucleus, okay? There's also nuclear fusion, which you can see is the last topic. This is actually something we don't do on a large scale here on Earth. Scientists have never perfected it, but it is what happens inside of stars, including our sun. And then in between, we're going to talk about Einstein's famous equation, E equals mc squared, because it really helps explain why fission and fusion produce so much energy. Because in both cases, mass is being converted to energy. And by the way, E equals mc squared comes out of the theory of special relativity. We don't really talk about any other parts of special relativity other than this one part, but it is interesting to note that this is actually kind of the culmination of a lot of ideas, including this idea that time and space are relative. Okay? All right, let's get on to defining what radioactivity is. Okay, so radioactivity results from radioactive decay. So we say decay because it means that some sample is becoming something else. So your sample of element X is becoming element Y. It's decaying into that other element, okay? So it is the process whereby unstable atomic nuclei transform and emit radiation. Okay, they transform into another element, into a different atomic nucleus. And we know what defines an element is the number of protons. So that means that radioactive decay must include a change in the number of protons, okay? Now, there's a type of radioactive decay that's kind of tied in that actually doesn't involve a change in protons, but it's always tied in with other radioactive processes that do involve a change in protons, okay? And it has existed longer than the human race. So it's been going on for billions of years since the early primordial universe. It goes inside the core of our own planet. It is just part of the physical web of the universe, okay? So it's not like a human created problem, for example, okay? So what is an unstable atomic nucleus? Or in general, what are unstable atomic nuclei? Well, they have an imbalance of neutrons to protons, okay? So the idea is that as elements get very heavy, they need an excess of neutrons. And if they don't have enough neutrons, then they start to fall apart. And sometimes they just inherently will start to fall apart just because they're too big. So this really applies to big elements, okay? And that would be big elements with a large atomic mass. And that you could say a large atomic number as well. But the idea is that, this is things like uranium, All right, a lot of nucleons in uranium, a lot of, over 200 total nucleons. Compare that to hydrogen that just has a single nucleon, just one proton. Uranium has over 200 nucleons in its nucleus. So it has a massive nucleus, and it's just inherently unstable because there's so many protons and neutrons that eventually they will just start falling apart. Okay? So that's what it means to be radioactive. So most radiation we encounter is natural, first of all, and it's background radiation that originates in the Earth. There's tons of radiation that comes from space because of these, again, heavier elements. That's because they have lots of nucleons, many protons and neutrons. We call them heavy elements. So cosmic rays are produced from the sun. So there are lots of cosmic rays are a type of light, by the way. And cosmic isn't to make them sound strange. It's just the classification of a very high energy photon. Okay, that's what a cosmic ray is. So there's lots of examples of radiation out there, lots of them, right? Again, on the surface of our planet, uranium is producing it. There are isotopes of potassium that are known to being radioactive. And not all radiation is in such large amounts that it's even harmful. I mean, life has evolved on Earth to handle a certain amount of radiation, okay? But radiation does become more intense as you leave the atmosphere. So as you go up in the atmosphere, you get exposed to more and more radiation. That's going to be primarily in the form of the light radiation. There's sort of a byproduct of other radioactive processes. But point being is that some places you're more protected from radiation than others. Space is particularly radioactive. That's part of one of the concerns of living in space or living on a planet like Mars without an atmosphere is that higher dose of radiation. Okay? So cosmic rays, this type of radiation that's associated with leaving Earth's protective atmosphere. And by the way, it's not just the atmosphere that protects radiation, although that certainly helps. It's also the magnetic field that allows the atmosphere to be so thick. So Earth kind of has this protective shield you can think of. Okay, we'll touch on that a bit more when we return much later in this book to astronomy. Okay, so cosmic rays are high energy particles. They are high frequency electromagnetic radiation. So when you say particle, think photon, because that's the particle we're talking about. And they are within the category of gamma rays. Gamma rays are the highest energy of the entire electromagnetic spectrum. Please review the electromagnetic spectrum if you don't remember where gamma rays fall relative to, say, visible light and X-rays, but they're right there. They're the highest energy. And on the very high end of gamma rays are a classification called cosmic rays. Okay, and they're just light with a lot of energy, very, very harmful to humans. Okay, so they affect us indirectly by transforming nitrogen atoms in the air to radioactive carbon-14, which ends up in plants we consume. So this is actually a really neat process because we'll come back to this when we talk about radiometric dating. Carbon-14 is constantly absorbed by every living organism. When an organism dies, there's a fixed amount of carbon-14 that then it continues to decay. So the older the dead organism, like a tree or a bone of a mammal, then you can find out how long ago it died because of how much carbon-14 is left. Okay, kind of neat. So the origins of radioactivity go back to military activities. Was it created by humans? Right? I said it wasn't, so you can rule that out. The Industrial Revolution? No, it wasn't human created. The beginning of the human era? I mean, that doesn't make sense. Before humans emerged on Earth? Absolutely. Okay. Again, for billions of years, over 10 billion years, there's been radioactivity. Our planet is about 4.5 billion years old. Radioactivity has been going on the entire time, and sometimes more than it currently is going on today. So when an atom undergoes radioactive decay, it A, becomes an ion of the same element, B, becomes an isotope of the same element, C, turns into a completely different element, or D, may or may not turn into a completely different element. Okay, so what's the best answer here? What have I kind of been touching on? Which ones can you rule out? Okay, so I want you to have a best guess here. So it turns into a completely different element. That's what radioactive decay involves. Okay. Now, again, there is radioactive emissions of these things called, basically gamma rays. That is just an excited nucleus that's relaxing. But the primary types of radioactive decay always involve a completely different element, which is to say, a change. Excuse me for that. A change in number of protons. Okay, because that's what a different element is. Elements are defined by the number of protons. Isotopes, if you recall, are just different numbers of neutrons for an element, a particular element. So you can have 6 protons, that defines a particular element. That particular element could have 7 neutrons, 8 neutrons, and those would be isotopes of that element. Okay, all right. But the point being, radioactive decay involves changes in the element. one element becoming another. So the types of radiation, the things that are actually emitted during that decay process because of an unstable nucleus, think of it as like jiggling around and sort of like shaking itself apart. So the things that can be produced are alpha particles, beta particles, and gamma particles. Okay, so alpha particles carry a positive electrical charge, so they're positive particles. Beta particles carry a negative, and then gamma has no charge because it's just light. Okay, we can test the charge of these emissions by having something like a sample. Radium is a naturally radioactive element that exists on the surface of Earth. And so you can stick it in here in a protective lead block. The idea there is that the lead block absorbs all radiation. Lead is really dense. That's why you have things like lead shielding, if you ever heard of that. But you could have an opening at the top, which allows the radiation out of that opening. If you run it through a strong magnetic field, that strong magnetic field will deflect charged particles, as we know back from our chapter on electromagnetic induction. And the positive particle will get deflected in the opposite direction of the negative particle, because the deflection depends on the charge of the particle. And the more massive alpha particle gets deflected less because it has more inertia. Okay, it's heavier, so it takes more force to turn it, and the magnetic field applies the same force. Okay, and then at least the same force per charge, and here there's twice as much charge, but a lot more than twice as much mass. Okay, and then over here, the beta particle gets deflected a lot because it has very low inertia. Okay, low inertia, which is to say low mass, because it turns out that the mass of the beta particle is exactly an electron. It's an electron that came from the nucleus, not where you'd expect an electron to come from. Okay, but electrons can be produced inside the nucleus through these decay processes. The alpha particle is actually just a helium nucleus. It's 2 protons and 2 neutrons, and it always comes in a chunk like that. You can never just have a single proton. You can have a single neutron, but in terms of common radiation, you always have 2 protons and 2 neutrons. Okay, and this was very massive because it's, each one is 1,800 times more massive than the electron, and there's 4 of them total, and it has a net charge of positive 2. Okay, and then again, gamma rays are just light that can be produced from an excited nucleus, kind of like the excitation levels we talked about for electrons outside of the nucleus. The same thing can happen for the nucleons inside the nucleus. They are also waves due to the quantum hypothesis. They are particles, but they're also waves, and as such, they can have these resonant waves, which are their energy levels. Okay, so let's talk a bit about alpha particles. They consist of 2 protons and 2 neutrons, which is a helium nucleus. We say it's a helium nucleus because that's what helium is, right? So helium-4 is 2 protons and 2 neutrons. What makes helium helium is also having 2 electrons. But if you ionize, which is to say strip the electrons away from helium, then you're left with just the 2 protons and the 2 neutrons, the nucleus, okay? But it has a special name. It's called an alpha particle because of how it was discovered, okay? They didn't know it was a helium nucleus, so they called it an alpha particle. We still call it an alpha particle today. Okay, so it loses energy quickly during interaction, can be stopped easily by a few pieces of paper due to its large mass and double positive charge. So it's going to interact very easily with other atoms, okay? So it's very easy to stop. Does not normally penetrate lightweight material, paper clothing, all right? So you don't really have to worry about it, penetrating your body. In other words, if we're thinking about the health concerns, it does cause significant damage to the surface of material, living tissue, due to its great kinetic energy. It has a lot of mass. So radiation burns absolutely can be associated with alpha particles, right, which is pretty horrendous. It picks up electrons and becomes harmless, helium, when traveling through air, right? So air very quickly just turns it into helium. And it deflects in the presence of a magnetic or electric field, of course, because it has positive charge, okay? A beta particle, on the other hand, is an ejected electron from a neutron. Because it turns out that there's these particular forces that hold neutrons together, neutrons being the only neutral particle inside of an atom, and that force can in some cases fail due to just the overall mass of the nucleus, and then that neutron can break apart into 1 proton and 1 electron, and the electron gets ejected. The proton stays behind. Okay? It has both a smaller mass and electric charge than the alpha particle, and it moves faster. It loses energy at a slower rate, okay, because it's so small, it kind of slips through, you can think of it, right? In air, travels further before stopping. It can be stopped by several sheets of aluminum foil, so it's significantly harder to stop. Clothing, paper will not stop it. Thick wood, metal will stop it, okay? It penetrates fairly deeply into the skin, potential for harming or killing living cells. So you can have serious cellular damage. That's where you can have these cases where people will actually just die from radiation poisoning, okay? Really, really gruesome stuff. Once stopped, it becomes an ordinary electron, right? So once it will then bond with whatever's around, or it will just come to rest inside of metal and become a free electron. It is deflected in the opposite direction to an alpha particle in the presence of a magnetic and electric field due to the idea of forces on charged particles. We know that there were different directions for the different particles, okay? We've known that back since our chapter on electromagnetic induction, okay? Gamma rays, the last particle that's produced from inside of the atomic nucleus, are high frequency electromagnetic radiation, okay? Which is to say they're high energy. They are emitted when a nucleus is in an excited state, as I said a moment ago, and it moves to a lower energy state. Okay, so it's the nucleus relaxing, and it usually follows other forms of decay. So you have alpha decay followed by gamma decay, or you have beta decay followed by gamma decay, especially alpha followed by gamma. All right. So it's more harmful than alpha or beta, which is kind of counterintuitive because it's the least massive by far. In fact, it's massless. Light has no mass. And because it's just able to penetrate so deeply. It penetrates very, very, very far. It has so much high energy. So, think about how UV light is harmful. It can give you a sunburn. Well, this is like UV light times 10,000. And so it's really, really harmful to humans, okay? So pure energy, greater per photon than in visible light, ultraviolet, or X-rays. It's unaffected by magnetic and electric fields. And the only way to stop it is thick lead shielding, okay? So it's stopped by lead and a thick amount of lead. So we're talking, like not a meter of lead necessarily, but many centimeters of lead. So you need significant amounts or about a meter of concrete, about 3 feet of concrete to stop a gamma ray. Okay, so which of these is the nucleus of the helium atom? Do you remember? Alpha, beta, gamma. Which one is it? It's alpha, okay? All right, so what holds the nucleus together? Because we talked about how the nucleus can fail and sort of rip itself apart, and that's just inherent to certain elements. And by the way, you're not going to find radioactivity in the light elements. I've said that before, but it's worth reiterating. If you look at, say, helium itself, or certainly hydrogen or nitrogen or oxygen, it's unlikely to find radioactive versions of those elements, okay? Because they're small enough that it's just easy for them to be stable. It's the big elements that tend to be unstable. That said, there are sometimes isotopes of the lighter elements that are inherently unstable, like carbon-14, which we mentioned, okay? But the point being that all those elements, the stable ones and the unstable ones, are all held together by the strong nuclear force, okay? This is the third force we've talked about, because there are 4 fundamental forces in nature. All of nature can be explained by those 4 fundamental forces. The gravitational force, discussed way back in an early chapter, the electromagnetic force, also discussed a few chapters ago, and now the third force that we've ever talked about of the big 4, which is the strong nuclear force. These are unique forces, okay? They're created by unique force fields. The fourth force is the weak nuclear force, which basically holds the neutron together. We're not really going to cover it here in this class. But suffice to say, the strong nuclear force is a very distance-sensitive attraction between nucleons. So it basically means that all nucleons, including protons and protons, are attracted to each other, which flies in the face of the electric force, because electric force says that protons should tear themselves apart. Right? 2 protons together should experience a repulsive force. But it turns out if you bring them really close, they actually are attracted to each other because the strong nuclear force is so much stronger. Notice here on this graph that shows insignificant to significant, if they're really close together, the strong nuclear force is actually stronger, not too much stronger, but significantly stronger than the electric repulsive force. So it actually prevents them from tearing themselves apart. It prevents the atomic nucleus from tearing itself apart. But if the atomic nucleus just gets a little bit bigger, if you take that spacing and triple it, for example, then at that point, the strong nuclear force just falls off almost immediately to 0. So it's not a force that falls off gradually. It does not have remember that 1 over r squared proportionality, the inverse square law that applies to both gravity and the electrostatic force? Well, that does apply to the electric force, but it does not apply to the strong nuclear force. Not at all. The strong nuclear force it has a very different mathematical function that defines how it permeates space. And it basically only exists on the scale of about 10 to the negative 12 meters, and then after that, it just goes to 0. Okay, so if this distance is greater than 10, say this is 10 to the negative 11, which is 10 times greater than 10 to the negative 12, then the strong nuclear force is almost completely at 0. It just goes away. Okay, at that point, well, now the electric force, which has decreased a little bit because the protons are further apart, but now it's way more significant. So now they will just tear themselves apart and they'll go flying off in opposite directions. So it's this really interesting force that only works at very, very close distances because, of course, 10 to the negative 12 is incredibly close. Okay, so the strong force is a force in a atom that holds the electrons in orbit, the nucleus that holds the nucleons together, or both. What does it apply to? Well, it turns out it just applies to the nucleus. It just holds the nucleons together, as we were talking about. It explains why the protons inside the nucleus don't just tear away from each other. Okay, good. Okay, so the presence of neutrons helps hold the nucleons together. All right, so it's accurate to say that the strong nuclear force allows two protons to be next to each other and not push off from each other, but nucleons really help, okay? Or other nucleons, particularly the neutral neutrons, okay? And so that really helps hold the forces together. So all nucleons, both protons and neutrons, attract each other. So having extra ones means extra attraction, all right? Only protons repel one another by the electric force, right? So you can definitely see why having extra neutrons would help hold the nucleus together, right? Okay, but in larger nuclei, far apart neutrons are less effective in holding a nucleus together. Because think about it, you got this proton over here, you got this proton over here, they're pretty far apart. This is the overall distance between them. That means that they start to feel primarily an electrostatic repulsive force, and all the nucleons total just don't create enough of the strong nuclear attractive force to keep the nucleus together. So that means the nucleus is just inherently kind of always about to tear itself apart, and occasionally will, with a chunk tearing off, often in the form of an alpha particle, two protons and two neutrons just popping off, okay? Or a neutron becoming a proton and emitting a beta particle, in other words, an electron, the processes we just talked about, okay? So that idea of that unstable nucleus inherently tearing itself apart means that there's a certain probability that that's going to happen, that these two protons are going to go flying off in opposite directions, for example, or maybe, they're going to carry two neutrons with them, okay? So that's interesting idea, right? There's a certain probability that's going to happen. Well, that probability then is tied into how long it takes for a sample of many of those atoms to have fewer of those atoms. And that's what a half-life is. So imagine you start with 100 atoms, all that are unstable. Well, after a certain amount of time, you only have 50 left because the other 50 have torn themselves apart, becoming a different element. They've decayed into a different element. The time it takes for half the original population to be left, well, that's what we mean by half-life. It's a measure of time, okay? It is the rate of decay for a radioactive isotope. It is the time required for half an original quantity of an element to decay into something else, is constant and independent of any physical or chemical change the atom may undergo. So like heating it up, or exposing it to a lot of light, or putting it in a chemical solution. None of those are going to affect it because it's happening inside the nucleus. It's really it's so internal inside the atom that everything that's happening outside doesn't affect it. Okay, which is great if scientifically speaking, because you have an independent process. Okay. And it can be calculated at any given moment by measuring the rate of decay of a known quantity using a radiation detector. Okay, that's how many particles are being emitted per amount of time. Okay, so let's consider a certain isotope has a half-life of 1 day. So it takes 1 day for the population to cut in half. In other words, to go from 100 to 50 in terms of the sample size, and those are really small numbers. Normally you have a lot more than 100 atoms. Well, that takes 1 day. That's the time it takes to go from 100 of the original sample to 50 remaining. Okay, that's what we mean by a half-life. Okay. This means that the amount of that isotope remaining at the end of 2 days will be what? Okay, so if it took us 1 day to go from 100 to 50, what will happen after 2 days? Think about this. What do we mean? We always cut the population in half, all right? 1/4, right? So in my example, there'd be 25 left because that's, of course, 100 divided by 4 is 25, right? After 3 days, we take 25 and divide it in half again, so then we'd have 12.5 and so on. Right? So each day we cut the population in half. In fact, it never goes to zero because you can continue to cut it in half. The sample's so big, it's trillions upon trillions, that you never actually get to that last one. Okay? So shown as a graph, we can consider a sample of 1 kilogram after a period, in this case, of 1,620 years. That's the half-life. And half-lives can be very long like this, many are. There would be half a kilogram left of the original sample. After twice that amount of time, 3,240 years, there's 1/4 kilogram left because it's 1/4 of the original sample. After 3 half-lives, see, because this is 1 half-life, 2, 3, after 3 full half-lives, which is 3 times 1,620 years, which is 4,860 years, there is an 1/8 left because we just divided by 3, or excuse me, divided by 2 3 times. So we take 1/2 and do it 3 times, right? Well, 1/2 divided 3 times, well, that's going to give us the 8th sample remaining. Okay, all right. So Radioactive isotopes decay, and by the way, you're not doing it, you're not multiplying it 3 times, you're actually raising it to the third power. So to be clear there, because if you just multiply by 3, you get 1/6. That's obviously not the same as 1/8. You have to raise it to the third power. Okay. So the shorter the half-life of a substance, the faster it disintegrates and the more active the substance. Okay. Think substances that have a very long half-life, there's not a lot of activity because it might take thousands of years or tens of thousands of years or even millions of years for the sample to reduce to half its original amount. Okay, so that idea of half-lives involves transmutation, because transmutation is just the name given of an element changing to another element. Now, there can be stimulated transmutation because you're bombarding an atomic nucleus of neutrons or something. We do that in laboratories. It happens sometimes in space as well during high energy events like supernova, stars exploding. But mostly, most transmutation that happens naturally is radioactive decay. Okay, it's the big nuclei or the particularly unstable isotopes of smaller nuclei that are tearing themselves apart. Okay, it's the changing of one chemical element to another, occurring in natural events or artificially in labs. All right, so here's an idea of crashing. This would happen more probably in a lab, or that can't happen under certain circumstances in nature. Crashing a neutron into a nitrogen nucleus and producing carbon and hydrogen. That's an example of transmutation. You produce something new. Right? So it's like the alchemist's dream, right? Turning lead into gold. It's possible. You can actually change one element to another. It just turns out it's a very high energy event, so you can't do it in a fireplace or even a big like melting pot. You need an actual modern physical lab with incredible amounts of energy, okay? Or you need to do it outside somewhere in space near a star or a black hole or something, okay? So natural transmutation, well, one example is alpha emission from a nucleus. So let's think about this, because we talked about mass number and atomic number in the previous chapter. Well, an alpha particle has 4 nucleons, which means whenever a nucleus releases an alpha particle, one of the 3 types of radioactive decay, it means its mass number will always decrease by 4 every time, because an alpha particle carries 4 nucleons with it, which means a mass number of 4. The atomic number will always decrease by 2, because that alpha particle carries how many protons? 2. Well, the atomic number is just the number of protons, okay? So the resulting atom belongs to an element 2 places back in the periodic table, right? Because it has 2 less protons. Now, so it will always be an element that's 2 less, but it will have an atomic mass that's 4 less, because it also carries those 2 neutrons with it. For example, uranium, which has an atomic number of 92, that's its place on the periodic table, has an atomic mass of 238. Notice the atomic mass is the number up top, okay? The atomic mass is the total number of nucleons, protons plus neutrons, okay? So when it releases that alpha particle, represented here as helium, because after all, an alpha particle is just ionized helium with 4 total nucleons and 2 protons, notice what's left. Thorium, so a different element, it's got an atomic number of 2 less, and it's got an atomic mass of 4 less, because of course 234 is 4 less than 238. See, that's what alpha emission is all about, okay? Beta emission from a nucleus means no change in mass number, because a neutron became a proton, right? A neutron became a proton. So the actual number of nucleons didn't change, and the mass number counts the number of nucleons, okay? No loss of nucleons. However, the atomic number actually increases. That's so interesting, right? You always expect it to decrease when you release something. But remember, the neutron released an electron and became a proton. Well, atomic number counts the number of protons. If a neutron becomes a proton, not mass number, but your atomic number goes up, right? So the resulting atom belongs to an element 1 place forward in the periodic table. Very interesting, right? And gamma emission from a nucleus means no change in mass number or atomic number. It's only the leftover excited state from another decay, and it's just that high energy. The only reason we really care about gamma emission so much, not because it's so interesting in terms of transmutation, it's just because it's so darn harmful, as we talked about, because those gamma rays are so hard to stop, okay? A bit about artificial transmutation. Ernest Rutherford had a cloud chamber, which is a device he created, and it had an experiment in 1919 that succeeded in transmuting a chemical element. After bombarding of nitrogen gas with alpha particles from a radioactive piece of ore, right, probably uranium, he found traces of oxygen or radium. But anyway, he found traces of oxygen and hydrogen. Since then, synthetic elements have been produced from atomic numbers 93 to 115. Right, we talked about all these higher ones being the unstable ones, all with short half-lives. Okay. So this is kind of a cool moment in history, right? The first time we were able to create something brand new, actually completed transmutation. Okay, so when an element ejects an alpha particle, the atomic number of the resulting element does what? Okay, so this is a good one that you should be able to kind of remember this and be able to answer this question. Okay, so alpha particle, what happens to the atomic number, not the atomic mass? Does it reduce by 2, reduce by 4, increase by 2, or increase by 4? Which is it? It reduces by 2 every time for alpha particle emission. When an element ejects a beta particle, the atomic number of that element reduces by 1, increases by 1, reduces by 2, or increases by 2. Which is it? All right, got your answer? Increases by 1. Okay, what happens to the mass number? Stays the same. Okay, so a certain element emits 1 alpha particle, and its product then emits 2 beta particles in succession. So here we have a series of radioactive emissions. Okay, and that's typical. They often come in series like this. The atomic number of the resulting element is changed by what? Okay, so we have an alpha particle. Right, alpha particle means we're going to have -2, right, during the first step, because we lose 2 protons, okay? And then we're going to have 2 beta particles, which means we have a +1 during the first one, and then the next successive one is another +1. Well, -2 + 1 means 0, right? Yeah. So we're going to be back with the same atomic number we started with. It'll have a different atomic mass, but the same atomic number. Pretty wild. Okay. So I mentioned that we can use this idea of half-lives to date objects, especially for carbon-14, because there's only so much left inside of an organism as that organism dies, because it's no longer absorbing carbon-14 in from the atmosphere. Think because like once you die, or any mammal dies, it stops breathing. If you're not breathing, then you're not absorbing new carbon-14. So however much is left inside of your body and is absorbed into tissue that's going to last for a long time, like bones, then that's going to slowly decay, and there'll be less and less in those bones over time. That's the idea of radiometric dating, especially for carbon-14. Okay, so carbon dating used for plants and animals based upon the ratio of carbon-12 to carbon-14. Carbon-14 is the heavier, more radioactive version of carbon. The half-life of carbon-14 is about 5,760 years, which is really good for dating things, kind of in that range of about 20,000 years, 40,000 years. It's great for, like, say, digging up a mammoth from the Ice Age, some 20,000 years ago, and finding out how old those bones are. Okay, so the method is not exact due to fluctuation in Earth's carbon-14 production. So it definitely has an estimate there. You can try to kind of compare between different samples and kind of figure out what were the natural fluctuations. That's continuing work by scientists, but it's an inherent error in the system. Okay. Non-living things dated through uranium and lead isotopes. Okay, so rocks, for example, you wouldn't want to use carbon-14 because rocks never absorbed carbon-14 to begin with, and they're going to be much older. So that half-life of 5,760 years just isn't long enough. Okay, if you want to say like date a meteorite, you need something that has a really long half-life. Well, uranium is good for that. Uranium decays to lead, uranium-238 in particular, that's the atomic mass, decays to lead-206. Uranium-235, a different isotope uranium, decays to lead-207. Okay, so an archaeological dig uncovers an ancient spear whose wooden handle contains 1/8 of the radioactive carbon of a fresh piece of wood. Okay, so this is using that carbon half-life. About how old is the spear? Okay, and remember, the number here is 5,760 years. Okay, by the way, the number here is on for uranium is on the order of 1 billion years. So much, much longer. But we're going to use the 5,760, so 5,760 years, and we have a sample with 1/8 of how much it started. So how many times do we have to multiply 5,760 by to get that idea of having an eighth? Because after 1 half-life, you'd have a half. After 2 half-lives, you have a fourth. After 3 half-lives, you have an eighth. Aha! So that means we should have 3 times 5,760, right? Indeed, that's it. You multiply, 5,760 times 3, and there you go. You get 17,280. Excellent. Great way to date things. Okay? All right. So, talked a lot about radioactive decay, big nuclei naturally tearing themselves apart. And we even talked about this idea of artificial transmutation, of crashing a small particle like a neutron into a nucleus and then producing something new. Okay? And all of these were made possible by the strong nuclear force. Okay, at least we discussed that a little bit in passing. Okay, now we're going to shift gears slightly and talk about nuclear fission and fusion, because this is a similar idea. It's all about the nucleus of an atom tearing itself apart. But in a way, it's more dramatic, because it's like it's taking a nucleus and having it really like split apart into 2 big chunks. Because you think about radioactive decay, the biggest thing that can be produced from the nucleus is the alpha particle, which has 4 total nucleons. But can you get that nucleus to say, literally rip in half and produce, one piece that has, say, 100 nucleons and another piece has 150 nucleons? Yes, yes, you can. All right, and that's called nuclear fission. All right, so let's talk about how that works. All right, so let's focus on a very common type of nuclear fission, which is using uranium-235, a type of uranium isotope that is particularly good to being torn apart. In this case, kind of like artificial transmutation, we take a neutron and we bring it in at high speed and crash it into a nucleus. Okay? When it does that, it in a cartoonish way, it's a bit more complicated after all. There's the quantum hypothesis and the idea that these particles are actually waves. So the physical model here isn't perfect. But the neutron, when it crashes into the nucleus, it causes a distortion in the shape. It really does. There is a change in the shape. And that change in the shape means that now we have protons that are very far apart from each other, so far apart that they're essentially are completely outside the range of the strong nuclear force, and they are only experiencing a repulsive force. And that's the tipping point, so to speak. Once those protons are so far apart from each other, they just start to continue to push apart from each other, and they tear the nucleus in half into 2 big chunks, okay? Each chunk with, in this case, about 100 nucleons, okay? Tearing it apart into krypton and baryon, right? Big elements, ripping that nucleus apart. And in the process, producing 3 more neutrons that just get freed. And that's just this particular process for uranium-235. Different processes have different side effects like this. And also producing a huge amount of energy because each of these particles has a lot of kinetic energy, especially what are called the daughter nuclei, which is the krypton and the baryon, okay? And so the idea there is that there's a lot of energy produced, a lot, okay? We'll talk about where that energy comes from in just a minute, but point being is that nuclear fission produces a lot of energy as the nucleus tears itself apart, okay? So the energy released is in the form of kinetic energy of the fission fragments, as I spoke about, that fly apart from one another, with some energy given to the ejected neutrons and the remaining given to the gamma radiation, because there's some light produced as well, okay? But most of it's going to be the kinetic energy of those big fragments, okay? So the idea is you have that critical deformation, okay? And then once it's, this kind of, barbell shape, it will just continue to tear itself apart. And that was all made possible due to the crashing of the neutron, okay? So by the way, the fact that uranium-235 produces 3 neutrons is a natural reaction of the uranium-235 nucleus tearing itself apart into those 2 daughter fragments. Well, that means that then each of those neutrons can go on to do the same thing if there's more uranium-235 around, not just a single atom of it. That's called a chain reaction. So it's a self-sustaining reaction in which the products of one reaction event stimulate further reactions, because each of those 3 neutrons that was produced then can go on to do 3 more, right? So you think about it, it spreads exponentially, okay? And if you keep some of those neutrons and make sure that they don't continue the chain reaction, as you can see here, some of the neutrons are wasted, so to speak. They just go flying off, not continuing. Then you can have what's a sustained chain reaction. That's what happens in a nuclear power plant. If you change the geometry of the sample and you allow there to be a lot more uranium-235 to go around, therefore there's a lot more opportunities for these neutrons to crash into another uranium-235 atom and not just escape, as is shown in the figure, well, then you have an uncontrolled chain reaction and you've got yourself a nuclear bomb, an explosion. So that's just the difference between the power plant versus the explosion, okay? And that ties in with the idea of the critical mass, just how much uranium-235 there is for the produced neutrons to crash into. So the minimum mass of fissionable material, fissionable just means it can break apart, in a reactor or nuclear bomb that will sustain a chain reaction, a mass large enough to sustain fusion, okay? At or above critical mass, in a large quantity of atoms, an enormous explosion can occur. So the idea, if you want to sustain the reaction, sustain fission, then you want to be right at critical mass, not above it, just exactly at it, pinpoint it. Okay, so obviously that has to be very accurate. But then if you just want it to blow up, then they're like, oh, let's just have twice the critical mass, and then you're going to guarantee you're going to get a huge explosion. Okay, so uranium-235, uranium-238, and uranium-239, all isotopes of uranium, are different what? Isotopes. I just said it. Sorry. Okay, but point being, that's what an isotope is. Okay, different numbers of nucleons. Okay, all right. Albert Einstein in the early 1900s, we're talking about him because we're going to talk about where that energy comes from in fission, discovered that mass is congealed energy. Okay, so again, he had this incredible theory, all started with the speed of light, and then came up with the idea that space and time are connected to each other. And then finally, that led to the idea that energy and mass are connected to each other. And that really energy and mass are one and the same. Energy can become mass, mass can become energy. Amazing stuff. Okay, he formulated the famous equation E equals mc squared, which is the key to understanding why and how energy is released in nuclear reactions, including nuclear fission. Okay, the idea there is that there's a loss amount of mass. There is more mass in the uranium-235 than in the total of all the products, the three neutrons and the krypton and the baryon. They don't total the original energy, the original mass. Some of the mass has disappeared. Where did it go? It became pure energy, mostly the kinetic energy of the big products of the fission, but also light, also the kinetic energy of the neutrons. Mass became energy. Okay, and that's what the equation is saying, because E is just the energy, M is the mass measured in kilograms. By the way, the energy we measured in joules, and then C is the speed of light, which is measured in meters per second, and we're squaring it. And the speed of light is a huge number. It's 3 times 10 to the 8 meters per second. So you can imagine if you square it, you get an even bigger number. So then you think about, you get a lot of energy for a small amount of mass. This number right here is so huge, such a huge number, that you can get billions of joules of energy just for a tiny amount of mass. There's a lot of energy tied up in mass. Okay, it's tied up in that strong nuclear force field. Okay, it's potential energy of the nuclear force. Okay, so the relationship of the equation terms, the more energy, this is for E equals mc squared, the more energy associated with a particle, the greater is the mass of the particle. The mass of a nucleon outside the nucleus is greater than the mass of the same nucleon bound in the nucleus. See, right? So the greater mass of the nucleon is evident by the energy required to pull the nucleons apart from one another. All right. Now that's going to apply to situations when you have a small element. Now there's also cases where with the big elements there's actually a loss of mass. Okay. So when the nucleons lose mass in a nuclear reaction, the loss of mass, which is the delta M, that just means change in mass. Remember, delta always means change, multiplied by the square of the speed of light, is equal to the energy release. The mass difference is related to the binding energy, that's of the strong nuclear force, all right, inside the nucleus. How much is required to disassemble the nucleus? Okay, so a graph of the nuclear masses versus atomic number of the elements from hydrogen to uranium shows an upward slope with increasing atomic number. Elements are more massive as atomic number increases, and that's because of an excess in neutrons. Because the heavier elements, like over here, like you say, uranium-235, just good example of a really heavy element, it has a lot more neutrons than protons, which is why the curve, which started off as just being a straight line, curves up. Okay, so you get a lot more nucleons in these heavy elements. So which of these nuclei has the greatest mass? Okay, which one? Which of these nuclei, total nucleus, hydrogen, iron, lead, or uranium? Well, it's got to be uranium, because there's a ton of nucleons there, and there's an excess of neutrons, so definitely way more massive. But what's interesting, if we divide the mass of the nucleus by the number of nucleons, this is the total number of neutrons and protons, then we get the mass per nucleon. And the mass per nucleon behaves very differently than the previous graph, okay? The graph of the nuclear mass per nucleon inside each nucleus versus atomic number from hydrogen to uranium. The greatest mass per nucleon is actually for hydrogen, all right? Because it has no binding energy to pull its mass down. All right, and so we have like hydrogen over here. Helium would also have a lot of mass per nucleon. As we get over to iron, iron has the least. Okay, iron literally has the least mass per nucleon. Its elements are held together weaker than any other, or its nucleons are held together inside its nucleus weaker than any other element. And then you get up to uranium, and it goes up again. Right, so at iron it bottoms out. You can see the graph kind of bottoms out right there, and then it creeps back up, but much more gradually than the decrease for the light elements, okay? And what's interesting is it creeps back up, it finally creeps back up to something like uranium, where now it starts to be more mass per nucleon. So that means that if you go in this direction from uranium, which is the direction of splitting things apart, which is fission, you produce energy. Because you're gonna be then losing mass, thus that mass becomes energy. You produce energy. Oh, a little technical error here. Bear with me. There we go. So you produce energy if you for heavier elements like uranium through fission. But obviously, that doesn't work for these other elements. If you took helium and split it apart, you'd actually lose a lot of energy because you'd end up with more mass per nucleon. You'd have to create that mass. So you'd have to actually put in extra energy to do fission of helium into hydrogen. So it'd be a really bad idea, right? It'd be physically possible, but it'd take a huge amount of energy to turn helium into hydrogen. But turning hydrogen into helium actually produces energy, and it does it through fusion. Because if you fuse, which means like bring together two hydrogen and make a helium atom, then that actually produces energy again. Okay? So everything that's lighter than iron produces energy through fusion. Everything that's heavier than iron produces energy through fission. And that's all about the mass per nucleon. Right? So it's just this incredible graph that dictates where energy comes from through nuclear reactions. Okay? So in which of these nuclei does the proton have the greatest mass? Hydrogen, iron, lead, or uranium? Which one? Because the proton mass doesn't stay the same because the proton is a nucleon after all. So the proton weighs slightly less depending on which element it's in. Well, where would it weigh the most? All right? Hydrogen, by far. There's no place where it has more mass. Okay? And which of these nuclei does the proton have the least mass? Do you remember? Where does the graph bottom out? You know, what's the one that has the least mass per nucleon? Lead, right? Or excuse me, iron, not lead, iron. If I called it lead a minute ago, I'm so sorry. Because iron is Fe, right? This is iron, right here. Okay. Maybe I was thinking lead shielding for radioactive, for radiation, but Fe is iron. Okay. So iron is the particular element. It's a famous element for that reason because it has the least mass per nucleon of anything in the universe. Okay. There's the graph. All right. So the idea then is if you have fission, like taking uranium-235, splitting it into barium and krypton, well, what you have now is you have less mass per fragment, therefore you produced energy. Okay? You turned mass into energy from E equals mc squared, as I spoke about. This is just showing it in a zoomed in way. Okay? On the other hand, if you have fission or fusion, the last one is fission, by the way. This is fission, splitting something apart. Okay? Fusion is bringing it together. Then you're also going to produce energy because you're going down the slope, okay? Because you're on this side of iron, okay? And then, so then you're going to have that opportunity to get energy because you have lighter nucleons, okay? So the graph of nuclear mass per nucleon versus atomic number for uranium, the nucleons in the uranium nucleus have more mass than the nucleons in the uranium fragments, right? Mass became energy. Okay, so finally, wrapping up with fusion, right? It is the combination of nuclei of light atoms to form heavier atoms, such as hydrogen forming helium, all right, with the release of much energy. And by the way, you can tell right away that because it's so much steeper here, the graph of mass per nucleon is so much steeper on the light side of iron for the light elements, there's a lot more energy in fusion than there is in fission, because the fission, it's a very gradual slope, so you have to really work hard to get that energy out of mass. Here, you get a lot of energy out of mass, okay? So any nuclear transformation that moves nuclei towards iron releases energy. Iron is the nuclear sink. You can't create any energy from iron, neither through fission or fusion. It's a dead end. So a graph of mass per nucleon versus atomic number for hydrogen to iron shows how the average mass per nucleon decreases from hydrogen to hydrogen to iron, okay? In this case, particularly becoming helium. Okay, so thermonuclear fusion, like that happens inside of the sun, is nuclear fusion is produced by high temperatures, resulting in more tightly bound nuclei. The mass decreases as the energy is released. This is analogous to a chemical combustion requiring a high temperature, where the end result is energy release in tightly bound molecules. Okay, it's happening at the nuclear scale instead of the atomic scale, because of course the molecules would be at the atomic scale or the molecular scale, and it's just a lot more energy. All right, so a solution is still being sought for reactors to occur under controlled conditions to provide an enormous amount of sustained energy. We've never been able to sustain it on Earth because it takes more energy to sustain the high temperatures than is actually produced. But we're working on it due to magnetic containment fields, and hopefully there'll be commercial fusion power plants in the future. So when energy is released by the process of fission or fusion, the total mass of the material after the event is less. Mass disappeared, it became energy. All right, so hopefully this chapter on the atomic nucleus and fascinating ideas like fission and fusion has been interesting. And well, we're finally ready to move into chemistry proper in the next chapter. So thank you so much for watching.